morning everybody. I am Sudhan Sharma and today we will be talking about a very important topic, the components of discrete mathematics and computer science. Hopefully the lecture which I am going to give you today will give you the flavor why to study a subject and what is the importance of the subject in studying mathematics, in studying computer science. Because generally we study a subject but we don't know what is the relevance of the subject and why the subject is to be studied and why our teachers are teaching the subject in our course. Say in computer science, generally students feel why we are taught about discrete mathematics, why we are doing numerical and statistical computing, and they don't have any relevance with the subject. So is there any relevance with the subject, or what are the components, and why only discrete mathematics is taken care and taught in computer science? That is the topic of concentration today. Firstly, starting the session, I would like to ask you people one thing, that was there any science before computer science? Of course, you will say, yeah, physics was there, maths is there, computers was there, and computers were not there, biology, and that means all these physics, maths, biology, chemistry are contributing to computer science. So how chemistry is contributed is that we will not be having any silicon wafers, and we were not having silicon, then we cannot be able to produce chips and all that stuff. Physics has identified the logic, and mathematics had built up the logic, the algorithmic part, the representation part of the logic. That means mathematics is mother of even core sciences, and it has contributed a lot while designing the algorithm, while designing the basis of the logic. So the mathematics is actually the core basis of all sciences. Now mathematics is categorized into two categories. The first and the foremost and the important category which is taught in computer science is your discrete mathematics. Why only discrete mathematics? Why not any other branch? The answer is that why human being was requiring computers. Human being was requiring computers because they want that there should be a uniform decision with the same type of situation. Now the decision can either be yes or no, true or false, high or low. That means only two levels are possible, nothing in between. And in order to maintain the uniformity of the decision, there has to be a science which should map the decisive part, and it is the discrete mathematics which map the decisive part, and hence the discrete mathematics forms the basis of our computer science. Secondly, what are the main issues, what are the main topics which are to be taught and which we are teaching you in your MCAs and BCAs? What is the relevance of those topics, where they are covered is to be covered now. Before discussing those parts, one thing I would like to discuss again, that how mathematics forms an interface in between the computer world and the real science world. You have studied the design and analysis of algorithm. Now what is an algorithm? Algorithm is a mathematical sequence of steps which is logically related. Now any real world situation which can be mathematized or which can be transformed into an algorithm, that means the sequence of steps which are logically related, only that algorithm, only that real world situation can be programmed. So that means before writing a program, we should be comfortable enough to write the algorithm in order to identify and understand the logic behind the solution, which is our program to be written. So again, this is the mathematics and the logical world which is forming an interface in between the computer world and the real science world. There are various topics in MCS 013, which is the discrete mathematics of MCA first semester. We are teaching you an important topic, a predicate logic and a proposition logic. You people are studying the predicate logic and the proposition logic, but you don't know where it is applied, what is the relevance of the subject. Let me cite you an example. At a single instance of time, a program which is delivered in Hindi in any other state might be delivered in any other regional language. How the computer is identifying and understanding that this program according to the region is to be delivered in a different language. or say in a Lok Sabha, somebody is speaking in Bengali and other person is not knowing Bengali, but he is understanding what other person is saying, and he is communicating in in the language and which is understandable by a person who is not knowing other person's language. That means there is language transformation. The predicate logic and the proposition logic contributes a lot to a field of computer science that is known as natural language processing. We will discuss this field today in detail. So this is one of the field of discrete mathematics which is contributing to computer science. Second field which is generally required and widely required in computer science is set theory. Set theory has wide dominance in database management system. We generally study relational database management system. But what do we mean by relation? How set theory is contributing to database management system? And set theory is a discrete component. How and why? Because an element may belong to a set or may not belong to a set. That means there are only two possibilities: whether belong to a set, whether it does not belong to a set. So set theory is a discrete environment. Similarly, predicate logic and a proposition logic is also a discrete environment. What do we mean by predicate and a proposition? Is a statement of mathematical interest which can be proved to be true or false. Now, it is a statement of mathematical interest which can be proved to be true or false. So, again only two situations are possible, nothing in between. That's why the predicate logic and the proposition logic is also discrete in nature. We are having other components, likewise probability, where we are having success and failure. We are having graph theory, and different things we will cover. One important topic is also Boolean algebra. Boolean algebra is dedicated to digital electronics. Without Boolean algebra, we will not be able to exercise and expedite the concept of digital electronics. And if digital electronics were not there, we will not be having any hardware component of our computers. And thus, we can say that it is a mathematics which is forming the basis of all the components of computers. Whether it is a logic, that means it is a software, or it is a hardware. The hardware component is generally dominated by our Boolean algebra and the digital electronics part. And logical part is further dominated by different disciplines which I discussed just now. Now, rather diverting to other topics, let's come to a precise one. Let's start our discussion with the predicate logic and the proposition logic. What is the difference between a predicate and a proposition? We had just now discussed that it is a statement of mathematical interest which can be proved to be true or false. So, then what is the difference between a predicate and a proposition? If a statement is talking about a person particular, then it is a proposition, whereas a generalized talk is related to the predicate. Say for an example, I give Ram goes. Now, in terms of predicate logic, the predicate part means the relation precede. What is the verb part of Ram? That he is going somewhere. So goes will precede. So I will cite you some example on the board. The predicate and proposition logic. What do we mean by proposition? Person particular. Okay. Particular, and this is taking care of the generalized aspects. So, cite an example. Ram goes. Now this is noun part and this is verb part, and the concept predicate means the relation precedes. So here Ram is performing some, that means generally the relation part is taken care by the verb. So in terms of this is an English statement, this is a real world situation. I want to do something, I want to produce a natural language processing environment which is understandable by computer. So it is already communicated to you that we need a real world situation which can be written in the form of algorithm. The algorithm can be transformed into computer world environment. So in order that the computer should understand what a person is saying, that Ram goes or whatever he wants to say, should be interfaced by a mathematical statement. The mathematical statement is governed by the predicate logic and the propositional logic. Here we will consider this as a proposition because we are talking specifically about a person Ram. If the statement was like this, that he goes, then we don't know who is he. That means it is generalized, and we will be here the statement is transformed from the proposition part to the predicate part. So keep this thing in mind, that relation precedes. So what is the relation? That is goes, and we are talking about Ram. So generally this syntax is followed by the programming language in artificial intelligence or natural language processing, which is named as Prolog. It is based on predicate logic, and this language utilizes this mathematical component of predicate logic to understand the English words to the computer. And now the thing will remain same, and he knows, the computer now understands the entity we are talking about is Ram and the relation we are talking about is goes. So the propositions are further classified into atomic propositions and molecular propositions. What do we mean by atomic propositions? Atomic propositions are the statements which cannot be further resolved, whereas the statements which can be resolved, can be further resolved, are the molecular statements. The example is Jack and Jill. Everybody has studied this poem, Jack and Jill went up the hill. Now what I want to say, the statement is molecular because it is contributing to two parts, Jack went up the hill and Jill went up the hill. Jack and Jill went up the hill is a molecular proposition because a proposition is a statement of mathematical interest which can be proved to be true or false. Now the statement can be a combination of more than one statement. A statement which is combination of more than one statement is a molecular statement. Now if I cite an example that Jack and Jill went up the hill, you see that the statement means Jack went up the hill and Jill went up the hill. That means there is a logical connective. There is a logical connective in between two statements. One statement is Jack went up the hill and other is Jill went up the hills. That means in order to make the computer understand how to logically relate two or more statements, we need logical connectives. The logical connectives which are taken care in predicate and proposition logic are categorized into following form: conjunction, disjunction, negation, implication, or which can be further also be double implication. So these all are connectives. That means using these connectives, conjunction is, the symbol is a cap, disjunction V, negation, the notation is tilt, implication, the notation is this, double implication, the notation is this. So these are the conjunction, disjunction, negation, these are the connectives which are used to produce the statement. Now, how can we connect more than one statement? At the same time, I would like to emphasize one thing more, that in propositional logic only connectives are there, only connectives. But at the same time, in predicate logic, we are having two components, one is connectives and other is quantifiers. Why we need quantifiers and what are the type of quantifiers? The quantifiers are categorized into two types. One is known as existential quantifier and other is known as universal quantifier for all quantifier. This is existential quantifier and this is for all, that means universal quantifier. Because the need of quantifiers is because the predicate logic takes care of the generalized statement. He goes or everybody goes. Now, he and everybody are the generalized statement. Then how can we use the predicate logic to state that a person particular is going or all of them are going? So in order to write some type of the generalized statements using mathematical component, we need quantifiers. So this is one of the differences. This is another difference. This is generalized, this is specific, this is having connectives and quantifiers, this is only having connectives. So at the same time, there is a relation in between the quantifiers and the connectives. What is the relation in between quantifier and a connective? If I want to say that the thing is for all, that means it is for me, it is for you, it is for you, and it is for everybody. That means this is for person A and person B and person C and person D. Now the AND part is actually this conjunction. If you had studied the digital electronics part, the AND part. What is AND? That this is for person A and this is for person B and this is for person C. So the for all part is actually taking care of the conjunction. At the same time, disjunction is taken care by existential quantifier. That means there is a person particular for which the thing is meant for which the action is meant for. There exists a person. There is a person which could be this or this or this. That means a person particular. So this is taking care of the disjunction part, that is this. At the same time, there is a logical hierarchy in between these connectives. What is the hierarchy? Hierarchy of operation. Firstly, we are having negation, then we are having conjunction, then we are having disjunction and exclusive OR part, exclusive disjunction, then we are having implication and then we are having double implication. The hierarchy goes in this way and in this way. That means if a sentence is there, firstly we need to take care of the negation part, then conjunction, then disjunction, and if a statement has both disjunction and exclusive disjunction, then first priority is of disjunction and then we resolve the exclusive disjunction. Firstly, a statement, otherwise if a statement has implication and double implication, then the higher priority is of implication and then is of double implication. This is the hierarchy tree for our connectives. Now, how we use these connectives, how we use these quantifiers in order to write statements of our daily life. Let me cite you some example. Say I write this example, there is a woman and she is mother of Eve. Now this is an English statement. Now in order to make the computer to understand this English statement, we need to write an algorithm, we need to transform this statement into a mathematical component which can be understood and which can be programmed for a computer. How we will write? There is a woman and she, this is generalized, this is also generalized. This woman is a particular part and she is a mother of Eve. Let me write the statement for this. There exists some x. There exists, this is a variable. This is a variable which is bounded. We can say it is a bounded variable. Bounded variable means we are talking about x. Who is x? X is of type woman. There exists some x. Who is x? X is type woman. If I say, if I use the statement comma y, I don't know who is y. So the variable y is not associated with the predicate. So this variable is unbounded. The variable is bounded because it is a predicate which is putting some boundation on the variable that this is the type. There is a woman and she is mother of Eve. Who? The relation in between. The relation precedes. Keep it in mind, predicate means relation precedes. X is mother of Eve. Now Eve is a constant. The relation in between the woman, which is X, and Eve is mother. So the mother part should precede. Now this is a mathematical statement for this English statement. There exists some x. X is of type woman and X is mother of Eve. So here we are using the logical connectives and we are using the quantifier part. Let me cite you one more example. These type of statements are in fact known as well-formed formulas. Well-formed formulas. Generally referred as WFF. This is very important and generally asked in the examination. Second thing is, every person has a mother. Now, every person, that means it is talking about for all quantifier. For all. Who are for all? All of type X. Who are X? X are of type person. If X is a person, this implies has a mother. If X is a person, that means X has a mother. Now, there is a problem. There is a problem with statement. The statement is, the problem is, we had not described y. What is y? So we can say modify it to x, y, and now we can say x and y both are person. This implies x is mother of y. Now y is also a person, x is also a person. That means every person has one mother. This is not possible because mother is itself herself a person. who herself has mother. So the function y, the variable y should not be there, and instead of that we should have a function which should be of x, where x is a person, because rather it should be like this, fx x. X is a person, this implies fx is mother of x, because mother herself is a person, she is also having mother and her mother is also having her mother. So person should be a function part where the function have a relation mother with x. Now this function is recursive, and here we had taken care of the connective implication and the quantifier for all. That's how we transform the English statements into mathematical statements. In the beginning of the session, I had conveyed you that we require mathematics, or we require discrete mathematics in computer science in order to make some decisions. So how the discrete mathematics help us to make decisions? It is very important to discuss this. In order to discuss this, we will discuss three topics, rather two, that is the tautology and the contradiction. In order to prove a statement, the proof can be direct or they could be indirect. So general a truth table is a common tool to prove a statement, and we are having the formulas also as a tool to prove a statement, because our discussion start with the topic that proposition and predicate are the statements of mathematical interest which can be proved to be true or false. The proof is, that means whether it is correct or not. So the tools which are generally available are the truth table and the formulas. Let's discuss the truth table part. Generally, how truth table is taking care of the same is, let me cite you some examples. De Morgan's law are generally influencing both Boolean algebra, the predicate logic, propositional logic, set theory. These laws are generally dominating more or less every component of the discrete mathematics. Let's restrict ourselves to the predicate logic and the proposition logic, and then we will prove by the use of tautology and the contradiction that how the truth table helps us to prove the De Morgan's law. What are the laws? In the case of proposition, the laws are categorized as negation A, conjunction B is negation A, disjunction negation B. Negation A, disjunction B is negation A, conjunction negation B. These are the De Morgan's law for connectives. But in predicate logic, we are having quantifiers also. So along with this, we are having the laws for quantifiers. The quantifiers, the relevance of the law is transportability or the transformability of one type of connective into another type of connective. Here we are transforming the conjunction into disjunction, the disjunction into conjunction. Because I had already stated that for all quantifier and existential quantifier are having the mapping with the conjunction and disjunction operator, so there has to be a transformation formula or transformation form, the law for our quantifiers also. The laws are What does this law say? This mathematical law says that this is not for even a single person of type X. X is of type P. That means anybody who is X and X is of type P, the thing is not available. So the thing is not available for even a single person. That means the thing is not available for any person. I hope you understand. The thing is not available for even a single person. That means the thing is not available for any person. So any is for all, or not even for a single person, is existential. I hope you understand that there is a transformation, the possibility of transformation from existential to for all, and similarly for this part. Now, the proof part of this takes care of the tautology and contradiction. The tautology section says the output should be entirely true, and if the output is entirely true, then the rule which we are discussing for is correct. If and all the values of the output are false, that means the entire rule is wrong. In order to have tautology and contradiction, the major role is played by the connective, which is known as implication. What do we mean by implication? If I say A implies B, those who had studied database management system might map this part with the functional dependency. In the artificial intelligence, we are having clauses, horn clause and all that stuff, all that part. Here we are having assumption, here we are having conclusion, the hypothesis, the conclusion. If this is true, this is true. Now, what does this mean? This is not A or B. They two are equivalent. It is very important. A implies B is not A or B. Second thing to be taken care is A double implies B. This means A implies B and that is a conjunction, B implies A. That means the thing can be resolved into not A or B, not B, so these two are important parts and generally used to prove the statements through tautology and contradiction. How? Let's see now. Let us first draw the truth table for A implies B itself. What does this mean? Not A or B. Not A, that means true. Or, what do we mean by or? Firstly, you should understand the conjunction and disjunction in order to handle this. The conjunction part, that is this, if A is there, B is there, A conjunction B, false, 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 true, true, false, true, true. Conjunction says all input must be true to have a true output. All inputs must be true for true output. All input, no, both are false. So false. All input must be true, but one is false, so output should be false. All inputs should be true. For true output, one is true, one is false, so again false, and here we will be having true as output. Similarly, so let's apply this logic of conjunction over here. So not A, how not A will work is, not A will take care of true, true, false, false. Now let's apply this. Or, that means the disjunction part says if any of the input is true, then output is true. That means A, B, A or B. That means A disjunction B. False, 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 true, true, false, true, true. If any of the input is true, then output is true. Both are false, output is false. One is true, output is true. One is true, output is true. Both are true, so output is true. So let's apply this definition of conjunction and disjunction over here. Now not A. A implies B is, by the definition, is not A or B. Not A disjunction B. So not A disjunction B. The disjunction says if any of the input is high, if any of the input is true, output is true. So this is, one of them is true, so output is true. Both are true, so output is true. Both are false, so output is false. And one is true, so true. Now you just monitor that in this situation only we are having false. That means if assumption is true, then conclusion cannot be false, because do not bother about this part, because we are concentrating on A and B, because A implies B. So if the hypothesis, if the assumptions are true, then the conclusion could not be false. And only in this situation A implies B, that means this does not imply A. If A is true, this implies this is true. So this is not possible. Under only this situation it could be false. Keep this truth table in your mind, or rather I will draw it again, and let's use this A implication part in order to identify the De Morgan's law, or to prove that whether it is a tautology or a contradiction. Generally students do some common mistake in proving the laws. So let's prove the De Morgan law. Not A conjunction B is equal to not A disjunction not B. So A not A, B not B. So this is false, 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 true, true, false, true, true. This should be true, this should be true, this should be false, this should be false, true, false, true, false. Now A conjunction B. What conjunction says? All the input must be high to have high output. All the input must be true to have true output. So A and A conjunction B. So A part, A and B. Please refer how we are drawing the truth table. All the input must be high. It is only this situation. So only this situation should be true and rest all should be false. That means negation and B will be true, true, true and false. This should be invert of this. Negation, negate part is there. Negate says output is reverse of input. So not A disjunction not B. What will be not A disjunction not B? Not A, the disjunction says if any of the input is true, then output is true. Not A, disjunction, not B. So this should be true because not A is true, not B is true, or that means this is true. If any of the input is true, then output is true. In this case, not A is true, but not B is false, but one section is true, so true. Not A is true, not A is false, not B is true. That means one section is true, so again true. At the same time, not A is false and not B is also false. That means that both are false, nothing is true, so output is false. What students do at this very instance of time when we ask the student that prove the De Morgan's law? Now the tool to prove a statement is either a tautology or a contradiction or a fallacy. So the thing is, the students do this. They compare simply that true is true, 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 and false, false. But this is not tautology. This is not leading to any conclusion. This is simply comparing that this is equal to this. But the rule says that this implies this. If this is the hypothesis, then this should be the conclusion. So if I rename this entire section as say P and this entire section as say Q, then the rule should be like this: P implies Q. Now refer to the implication table. Refer to this implication table. When A is true and B is false, then only false is there. In all other situations, the output is true. So true, true, that means A is true, B is true, then not A or B, that is A implication B is true. So same will be happening over here. This is now referred as P, this is now referred as Q. Map this table with now this section. Map this table with now this section. True, 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 and true. Again, for all the same, it will repeat true, true. Now refer to this part. False, false. What is happening in this table? False, false, true. Yes. Now the conclusion is tautology. Now the conclusion is tautology because every output is true. And when every output is true, that means the statement which is under consideration is correct. Please do not do this type of mistake in your examination because this will deduct your marks. Try to transform it into the form of tautology or a contradiction. We have many more things in the discrete part. Likewise, we are having the set theory part, and we had discussed this predicate logic and the proposition logic. After referring to this section, hopefully you will be able to identify the differences in between the predicate logic and the proposition logic. At the same time, you will be correctly able to identify how to prove a statement of a mathematical statement of a mathematical interest. One more thing which I would like to tell you is that there is a difference in between a theorem and a predicate and proposition. Generally, when you study, you don't know. The theorem is a statement which is true. A theorem is a proposition which is true, which can prove to be true, whereas proposition and predicate are the statements which can be proved to be true or false. So theorem is a special case of predicate and proposition. After going through this lecture, I hope you got an idea where is the application of the predicate logic and the proposition logic in computer science. It is applicable to natural language processing for artificial intelligence. It is applicable to Boolean algebra and digital electronics. So it has got wide acceptance, wide application, and I hope this lecture will be fruitful to you. Thank you.
Know that there is